In this video, we're going to look at base conversion. That is how to convert any whole number from decimal to binary and other bases.
Namaste, my name is Ravi Reddy and welcome to my new video series entitled A Prequel to Programming. Things you should learn before you write your first line of code. Here I'll be trying to explain the fundamentals of computing and coding which are needed before you write your first line of code.
First, let us look at how to convert a decimal number to decimal number. This is just to understand the basic idea behind base conversion. So we start with the number 163 and we divide with our base, which is a decimal base 10. So we get a quotient of 16 and we get a remainder of 3. Next, we divide that 16 by 10, we get a remainder of 6 and a quotient of 1. Next, we divide this 1 by 10, we get a remainder of 1 and we get a quotient of 0. So when we get a quotient of 0, we stop. So now if we check these digits, 1, 6, 3. So obviously 163 in base 10 equals 163 in base 10. Nothing new here, but we understood the process. In the first step, we filtered out the units place of the number. In the second step, we took out the tens place, that is 10 to power 1. And in the last step, we took out the hundreds place, or that is 10 to power 2. That is the idea I wanted to show in this conversion. Now let's look at converting decimal to binary. We again take the same number 163, divide by 2, we get a remainder of 1 and a quotient of 81. Then we divide 81 by 2, we get a quotient of 40 and a remainder of 1. This is the next step, and the next step, and the next step, and the next step. Finally, we are left with a remainder of 1 and a quotient of 2. Final one more step, we divide 2 by 2, we get a quotient of 1, remainder of 0. And when we divide 1 with 2, we get a remainder of 1 and a quotient of 0. Here's where it stops. So we say that 101000011 is the binary equivalent of the number 163 in base 10. We take these digits from bottom to top. As you can see here, 101000011. Next, let us try to convert a decimal number to base 5. Just to understand, the process is same for all bases. We divide 163 by 5, we get a quotient of 32 and a remainder of 3. We do the next step, we get a quotient 6 and a remainder 2. Next step, we get a remainder 1 and a quotient 1. The next step, we get a quotient 0. We stop here. So 163 in base 10 is 1123 in base 5. And you can see that if you again multiply this with the place values, this is place value 5 to the power 0, which is 1. The place value of this number is 5. The place value of this place is 25. And the place value of this is 125. So you can see that 125 plus 25 is 150, plus 5 into 10 is 160, plus 3, 163. That's what we started off with. Next, let's convert a decimal number into base 16, which is also known as the hexadecimal base. We divide 163 by 16, we get a remainder 3 and a quotient 10. We divide 10 by 16, we get a remainder 10 and we get a quotient of 0. Now, how do we represent this remainder of 10? For this, we have to look at hexadecimal digits. What we have is that in base 16, we map the number 0 to 15 to these digits 0 to 9 and then A, B, C, D, E, F. So the new things we have to learn is that in hexadecimal, the symbols A, B, C, D, E, F stand for the values of the decimal 10, 11, 12, 13, 14 and 15. And these same values when convert into base 2 are these values. 1010 stands for 10. You can see that this is 8 plus 2, that is 10. Similarly, B stands for 11, C stands for 12. You can see that this is same as 8 plus 4 is 12. D stands for 13, E stands for 14, F stands for 15, which is 8 plus 4 plus 2 plus 1. So these are the hexadecimal digits. So now we can write this value as A, and this is 3. So the value 163 in base 10 converts to A3 in base 16. Let's look at some examples of base conversion using this small Excel sheet which I prepared out here. So let's try some numbers out here. Let's take 100 and let's say what does it look like in base 16. That is a hexadecimal base. So that becomes 64. As you can see, if I divide 100 by 16, I get a quotient of 6 and a remainder of 4. Then when I divide the next time, I get a quotient of 0 and I get a remainder of 6. So that is 64. What is the value? 255 in base 16. It is FF. That's the largest 8-bit number you get. Let's see the same value in base 2. In base 2, it is 11111111. Let's see what is 127 in base 2. It is 1111111. Let's take 172 in base 2. This is the number 10101100. The same number, if I take it in base 8, becomes 254 in base 8, and in base 16, which is hexadecimal, becomes AC. I could also use an odd base like 5, which I showed in the earlier example. 172 would be 1142 in base 5. This Excel sheet is available for download at the link given below the video. Please download and play around with the Excel sheet so that you can become more familiar with base conversions. Now that we have seen how to convert from decimal to binary and hexadecimal, all of the bases, let's go back and look at a simple problem of converting binary to base 4. So that means we are converting from base 2 to base 4. So this is a very simple process. You simply take the binary value and split the digits in groups of 2. This is 2, and these 2, and these 2, 2 digits, 2 digits, and 2 digits, and write down their equivalent in base 4. So this becomes 1, this becomes 3, this becomes 3, this is 2, 1, 1, 1, 1. So this becomes 1, 1, 2, 3 in base 4. Similarly, when we convert binary to octal, we have to group the binary digits in groups of 3. 3 digits, 3 digits here, 3 digits here, 3 digits here, and 3 digits here. And write down the octal equivalent of each of the patterns. So this is here 4 plus 1 is 5, 4 plus 2 plus 1 is 7, 4 plus 2 is 6, this is a 2, and this is a 5. So the binary pattern 1010101101111101 in octal comes out to be 52675 in octal. Now let us see how to convert binary to hexadecimal. We simply group the binary digits in groups of 4. This is 4 digits, 4 digits, 4 digits, and the next 4 digits. And then we take the hexadecimal equivalent of each group of 4 digits. This is a D, B, 5, 5. So this binary pattern converts to 5, 5, BD in hexadecimal. In the same way, we can expand from hexadecimal back to binary. If you are given A3, F8 in base 16, we simply expand each of the digits into its equivalent 4-bit pattern. So that's what we are doing here. Each of these hexadecimal digit is expanded into its binary equivalent. In the same way, we can also do from octal to binary. We convert each octal digit into 3 binary digits as we are done here. 5 becomes 101, 1 becomes 001, 3 becomes 011, 7 becomes 111. That was a brief introduction to base conversion, how to convert whole numbers from one base to another.
Please subscribe to my channel and hit the bell so that you will get notifications of my future videos. Thank you.